Hello, my name is Charles Cassette, and this video is a brief presentation about relative position estimation between two UWB devices, which also have IMUs. This work focuses on the problem of estimating the three-dimensional relative position of one robot relative to another. In robotic teams, this information is crucial for the robots to execute tasks autonomously. Examples include collaborative exploration, mapping, formation control, and search and rescue. More specifically, we consider the following scenario. Imagine there are two robots. They are drawn as quad rotors here, but this is applicable to any robot. From now on, we'll arbitrarily take the perspective of the red agent. Suppose each robot is equipped with an inertial measurement unit and an ultra-wideband radio transceiver. The inertial measurement unit consists of an accelerometer, a rate gyro, and a magnetometer, while the ultra-wideband transceiver is capable of measuring the distance between itself and the other transceiver on the blue agent. Note that the ultra-wideband transceivers are just one example of a sort of distance sensor, but this work is not specific to ultra-wideband. Rather, the presence of distance measurements between robots in general. The problem is now to obtain a full three-dimensional relative position estimate of the two agents using only these measurements, which are also corrupted by noise. The literature lacks a comprehensive three-dimensional solution for such a minimal set of sensors. The main challenge associated with this problem is that it is impossible to determine the position of the blue agent from only one distance measurement. In 2D, if the blue agent were located anywhere on the circle around the red agent, it would produce the same distance measurement. It could be here or here. And all three of these cases would produce the same distance measurement. Our solution to this problem considers the information from previous distance measurements. In this diagram, if the blue agent were to move at all, then this would change at least one of the distance measurements. Hence, the position corresponding to this set of distance measurements is unique. This will lead us to use a sliding window filter, which is a framework that incorporates multiple measurements at once, as opposed to something like an extended common filter, which only considers a single measurement at a time. We call these special instances in the agent's history keypoints, and we draw them as green diamonds. One issue we now face is that the IMU and distance measurements actually occur much more frequently than displayed on the graphic. To see why this is a problem, imagine that we simply take the 5 most recent distance measurements as key points, which is what a plain vanilla implementation of the sliding window filter does. In this situation, the blue agent could actually move in and out of the screen while still producing the same distance measurement. If the key points all lie in a straight line, we lose the observability of the relative position. Therefore, we must deliberately access older measurements and create an estimate for the trajectory between them by integrating the IMU measurements. A technique called IMU pre-integration allows us to do this with virtually no addition to the computation time. Finally, as explained in the paper, we propose a quick and simple method to find optimal key point locations. This makes the position estimate as precise as possible. The simulation shows our algorithm in action. With realistic noise values, our algorithm achieves an accuracy of less than 40 centimeters. It is also quick to execute and easily decentralizable. We also tested our method with real sensors. Since this was only a state estimation task, it was simpler to construct a small device that contained the relevant sensors instead of actually flying quad rotors indoors. We walked around our lab, collecting measurements between two identical devices, while also collecting ground truth position attitude data using an optical motion capture system. Experimental results show that our algorithm yields a 2 to 3-fold reduction in position estimation error, compared to a plain vanilla implementation of the sliding window filter and a standard extended common filter. Although these two other solutions could perform well in theory, they are not as robust to practical issues such as measurement outliers and magnetic perturbations. This concludes the presentation. Thank you and take care.